Hello everybody, today we're going to talk about dimensional homogeneity or dimensional analysis, and what that is it's a tool to help us analyze equations. If an equation is not dimensionally homogeneous, then there's some red flags, there's a problem with our algebra, derivation, things like that. So it's kind of like a check tool, and so we'll talk about what dimensional homogeneous means here. We're going to dive right into it and talk about this equation, the force equation, use it as an example. The force equals mass times acceleration. And so the variable form is F equals ma, and we're going to apply some newtons to it because dimensional analysis analyzes the dimensions of the equation. So we need dimensions to work with. So the SI units for the force equation is newtons equals kilograms times meters per second squared. And so the first thing that you do when you do a dimensional analysis on an equation is you're going to remove anything that's not a dimension. So values, variables, all of that goes away. And when you remake your equation, you get something like this. So here we have Newton times kilogram, or equals a kilogram times a meters per second squared. And it looks kind of funny, but everything still applies. The equal sign rules, the multiplication rules, division rules, all of those still apply. And what you're doing to see if an equation is dimensionally homogeneous is you're going to make sure that the right-hand side and the left-hand side of the equation equal each other dimensionally. So we can't really do that yet because we have what's called a derived unit on the left-hand side and base units on the right-hand side. So base unit's what we want, okay? Everything should be in base unit form, and a base unit is something that can be broken down. So a kilogram is a kilogram, a second is a second, meter is a meter. But a newton, being a derived unit, is derived from everything on the right-hand side of the equation, the kilogram meter per second squared. So we need to break this down into base units before we can actually make the assessment of dimensional homogeneity, or make the assessment that the right-hand side equals the left-hand side. So we're going to replace the newton with its base units, which is kilogram meters per second squared, and we can now assess that the right-hand side and the left-hand side of the equation are the same. Pretty simple, right? I'm actually even going to take this a step further, do some simplification, and we get kilogram equals a kilogram. And so what this has done is it has proven that our equation up here is dimensionally homogeneous. It is a true logical statement. So if this was, for instance, a meter instead of a kilogram, so we had kilogram equals meters, this would be a false logical statement. And what that does is it throws up red flags. It says, hey, something is wrong either with the derivation, with the algebra, substitution, something went wrong that's making this logical statement false. If a logical statement is false here, the equation is not valid. You cannot use it. So this is a really good tool to use to check whether you're in school, in the professional world, to make sure that an equation has dimensional homogeneity. So we're going to do a little example. Let's say that we're an engineer and we want to check this rod here. So this rod was designed with a certain cross-sectional area right here, and it's supporting this cube, this 50 kilogram cube that's producing a weight force on the rod. So in order to make sure that this rod's not going to break, we're going to calculate the stress. And if you haven't done anything with stress yet, don't worry about it. Stress is another fancy word for pressure, which is a force divided by an area. We're just using it as an example right now. So here we have our pressure equation, F divided by A. So when we plug all of our values in, we have our force in the numerator and we have our area in the denominator, we get 245,000 pascals. That sounds like a lot of pascals. It's actually not. The pascal is a very small unit of pressure. But I compare it with my charts and I say, yep, this pressure is lower than the threshold of this rod, so we're good to go. But before we go to our boss and say, hey, I did the calculations, we're all ready to go, you're a good engineer, so you're going to do a dimensional analysis to help verify this equation. So just like we did over here, the first thing we do is we remove all the values and any variables and just leave the dimensions. So here we have the equation rewritten with just the dimensions, and so we do our simplification and we get this guy. Now before we can determine if it's dimensionally homogeneous, we need to make sure everything's in our base units. So the left hand side, seconds, meters, and kilograms, all of those are base units, but our Pascal, that is actually a derived unit. So we need to break that down. So breaking it down, we know a Pascal is a Newton per meter squared. Meters is a base unit, but again, we have another derived unit. We have a Newton, so we substitute this in for the newtons to get all base units. And we do, in fact, have a homogeneous solution. The right-hand side and the left-hand side equal each other. And so this is a true statement. So it's really important to remember that this does not mean that this is a correct answer. This just means that your dimensions on the right-hand side and the left-hand side equal each other. And it solidifies your equation. If this was false, then you definitely know you have a problem here. But just because it's also true does not mean that your solution is true. You need to make sure you do your math correct. So now we're going to talk about a really neat subject. Don't let it scare you if you haven't done drag yet. We're just using it as an example. It's just a really beautiful example of dimensional homogeneity. So here we have Mom's minivan, right? And Mom's minivan is traveling to soccer practice, got the kids in the car, they're late, they're traveling fast. So here's the air moving past the car, right? It's going on the sides and over the top. And what it's doing is it's producing a counterforce to the motion of the car. It's actually making the car work harder to travel at that speed. And this drag force was calculated first by John Strutt. He's the one that's accredited with developing the drag equation. And his story on how he does it, I cannot confirm. I looked for sources for it and I couldn't find it, but it's just a really good story to share about dimensional homogeneity. So what John did is that he first identified what drag was. And he said that drag was a force. I move my hand through a liquid or a fluid, I feel a force on my hand. So he also said that the faster I move my hand through that liquid or fluid, the more force I feel, so it must be a function of velocity. He also said that's a function of density because if he moves his hand in water, there's a greater drag force that he feels versus moving his hand through air. And then finally, he says that it's also a function of the cross-sectional area, because when he moves his hand in water with a finger instead of his whole hand, he feels less drag force. So the more area you have, the greater the drag force. So this is his equation, his first stab at it. So in order to verify this equation, he performed a dimensional analysis, removing everything except for the dimensions. Here's his equation. He did his reductions, and he is left with this equation. And then we can see just right away that this is a false equation. The left-hand side does not equal the right-hand side. So when he saw this, he automatically knew that this equation right here needed to change. There was something wrong with it. But he noticed that the right-hand side of the equation is missing a meters per second, right? That's what's missing from the right-hand side. So he said meters per second is a velocity. The only velocity within the system is the actual wind velocity or fluid velocity. So what he did is he actually squared it. He squared it to add that extra meters per second into this equation, and then he did another dimensional analysis to see what it would do. And so here you have your force, you have your velocity squared, your density, and your area is right there. And doing your reduction, you are left with this equation. And this equation is indeed dimensionally homogeneous. The left-hand side equals the right-hand side. And so what's really interesting about this is the final drag equation that we use even today is so close to what he got. The only difference is that we have this CD here, which is a drag coefficient. It takes into account like the shape factor and the different surface finishes of the vehicle that affect your drag, but it's a dimensionless coefficient, which is why it didn't come up in his dimensional analysis. But he was very, very close, and we still use this drag function today. So this right here is dimensional homogeneity. It's very, very useful as it was for John. It can tell you if your equation is wrong, if something was not performed correctly. It can definitely put up some red flags for you. So when you do dimensional analysis, you need to remember some things, and this is some things that I've noticed when I teach dimensional homogeneity to people, is that they always forget sometimes that variables are not don't have dimensions, just like this drag coefficient here. It did not have a dimension. So when you do a dimensional analysis, you just leave that part out. You don't add any dimensions because it doesn't have any. Here are a couple other units or variables that have that don't have dimensions. You have the Mach number and also the Reynolds number, which is a famous number in fluid mechanics. So another thing you need to remember, exponential laws usually trip people up the most when you're doing dimensional analysis. So this is an equation actually I was given back in college. My professor gave it to us, and basically it calculates the fluid velocity of a fluid rolling down a hill inside of a pipe. So it's gravity fed. So you have the radius of the pipe, and then you also have the slope of your hill, and then you have this descriptive constant. And what he asked us to do was to find the units of this descriptive constant. It could be unitless or it could have units. We didn't know. So we did a dimensional analysis, and I'm just going to point out here, slope doesn't have units, so I just put in a 1 there just to show that that's where it would go, but it really doesn't have any units. But what tripped a lot of us up was that the reduction between the meters on top and the meters to the 2/3 power on bottom. So you need to make sure that you got those exponential rules down right, because this actually happens quite a bit in dimensional analysis. As you can see, this descriptive constant actually is kind of just some weird units, doesn't really mean anything, but those are the actual units of this constant. So keep those in mind. That's dimensional homogeneity for you. Hopefully that you guys can practice it and get really good at it, because it is a useful tool, and happy calculating.